We're jumping straight in today with a really critical paper from Lewin and colleagues. It's called Quantization Hurts Reasoning, an empirical study on quantized reasoning models. And it tackles this core trade-off that everyone in ML engineering is facing right now. You've got these incredible reasoning models using chain of thought or CoT.
Which is amazing for performance.
Exactly. It's why models like DeepSeek R1 are so powerful. But the flip side is this huge inference cost. The model is spitting out hundreds, sometimes thousands of tokens.
So you think, okay, let's quantize it. Let's reduce that numerical precision to save money and speed things up.
But then you have the risk. What if all those tiny errors from quantization just accumulate over that long reasoning chain and your final answer is completely wrong?
It's a huge gamble. And this paper, for the first time, really maps out that risk. They give us a clear guide. In fact, they boil it down to 6 core insights, which we can run through really quickly.
Okay, let's do it. The rapid fire summary.
First up, the safety zone. 8-bit weight activation KV cache quantization, what we call WA8KV8, is basically lossless. You're looking at an accuracy drop of less than 1%, guaranteed.
And for weight only.
4-bit weight only, so W4A16 is near lossless. Very safe territory as well. Second, your toolbox. For weight only, you want to use AWQ. If you absolutely have to push to 4-bit for everything, flat quant is your best bet.
Okay.
Third, risk assessment. This is a big one. The harder the task, the more quantization hurts. A super complex task like AME 120 could see up to 4 times more performance degradation than something simpler like GSM 8K.
So your use case really matters.
It's paramount. Fourth, pedigree matters. How a model was trained distillation versus reinforcement learning, and even what family it comes from, like Quen versus Llama, creates totally different sensitivities to compression.
Interesting. What's number 5?
Output length. Good news first. Models with only minor accuracy drops don't start rambling. They keep their outputs short. But if you get really aggressive with low-bit quantization, the model does generate longer outputs to try and compensate. We saw that a lot in smaller 1.5 billion parameter models.
And finally,
the scaling payoff. This is the big strategic takeaway. A larger model, say 32 billion parameters, that's been quantized down to a low precision, can give you way better accuracy and latency than a smaller 7 billion parameter model running at full precision.
Okay, that gives everyone the high-level map. So let's dig into the details, starting with that motivation. The whole reason for this work is that quanta reasoning creates just a massive inference overhead.
It really does. I mean, DeepSeek R1 was a proof of concept. It showed that long, complex reasoning chains work, but it came at a staggering computational cost. The whole point here was to figure out, with precision, where does that reasoning chain actually break when you start injecting noise from quantization?
To build a proper risk profile.
A real risk profile, exactly. And to do that, they had to be incredibly thorough with the setup.
Right. They couldn't just test one model or one algorithm.
No, this was comprehensive. For models, they looked at everything from the DeepSeek R1 distilled Quen and Llama families, all the way from a tiny 1.5B model up to a 70B giant.
And they included different training styles too, right?
Yep. They had RL-trained models like QWQ32B in there next to standard ones like Quen38B. The idea was to get findings that could actually generalize.
And the quantization methods weren't just theoretical.
Not at all. They were testing everything. Weight only, just the KV cache, and then the full joint weight activation KV stack. Yeah. And they use the tools people are actually deploying right now. AWQ, GPTQ, smooth quant, flat quant. The state of the art.
Now, to really stress test these models, you can't just give them a simple summarization task. What were the benchmarks you used to find the breaking point?
We needed tasks that demanded genuine step-by-step logical deduction, things where CoT is non-negotiable.
So really hard math problems.
Exactly. The toughest were AIM 120 and Math 500, which are basically competition-level math. Then we had scientific Q&A with GPQA Diamond and coding with Live Code Bench. We also included GSM 8K, but that's more like primary school math. It served as a useful baseline for easy reasoning.
That variety lets you see exactly where the error starts to pile up.
Precisely. It's in those long, hard problems.
Okay, that sets the stage perfectly. So let's get to the practical advice. For the engineers listening, what bit widths can we actually use safely? The paper defines lossless as a drop of 1% or less. What's the fire and forget guaranteed safe option?
The absolute safe harbor is 8-bit, W88KV8. For joint quantization of weights, activations, and the KV cache, this was consistently lossless across every model and every task.
No exceptions.
No exceptions. The best algorithm had a drop between 0 and 0.6%. So if you're deploying a reasoning model and you absolutely cannot tolerate a performance hit, you stick with 8-bit.
But everyone wants to push lower. Everyone wants 4-bit for that maximum efficiency. So how risky is it to go all the way down to W4A4KV4?
That's where the red flags go up. The noise just becomes too much, especially for the smaller models. We saw the 1.5B and 7B models just collapse. Accuracy drops of over 10%.
Wow, that's unusable.
Completely. Even on a big 32B model with the best possible algorithm, you're still taking a nearly 3% accuracy hit. It just seems small models don't have enough parameters to absorb that much compression noise. Frankly, making 4-bit WAKV reliable is probably the biggest open challenge in the field right now.
That makes a lot of sense. So what if you compromise? What if you only quantize the weights and leave the activations and KB cache in high precision?
That's a much safer bet. For weight only, 4-bit with something like AWQ is incredibly robust. It's almost lossless. On the 32B model, the drop was a tiny 0.4%. That's often the sweet spot for reducing your memory footprint.
But you can still push it too far.
Oh, definitely. Dropping to 3-bit weight only is still a bad idea. The 1.5B model, for example, dropped over 7% there. There's a clear cliff.
Let's focus on the KV cache for a second. That's so critical for managing memory with these long COT sequences. How low can you safely go there?
This was a really encouraging result from the study. For the bigger models, so 14B, 32B, you can take the KV cache down to 4-bit and it's effectively lossless.
Even on those super long context tasks.
Even on AMI 120, where the model might generate over 10,000 tokens, the fact that 4-bit precision in the KV cache can handle that without significant degradation is a massive win for anyone trying to deploy these things.
Let's talk tools. For 4-bit weight only, the paper recommends AWQ over GPTQ. They often get similar accuracy, so what's the reason for that preference?
It really comes down to robustness and efficiency. AWQ is it's a cleaner approach. It deals with outlier channels before quantization by scaling them. GPTQ, on the other hand, relies more on the calibration data you feed it after quantization to fix the errors.
So AWQ is just more inherently stable.
It's more resilient, yeah. It makes it easier to deploy because you're less worried about whether your calibration data is perfect.
And for that full WAKV stack?
For 8-bit, honestly, anything works. Smooth quant is great because it has 0 overhead.
Right.
But when you get into that really tough 4-bit WAKV space, flat quant was the clear winner. If you have to go there, flat quant is your best option. It dropped 2.9% on the 32B model, while the next best, MXFP4, dropped almost 12%. It's not even close.
I remember reading about a very specific edge case with the Quen models and the KV cache. Something about Quorot just failing catastrophically.
Yes, this was a fantastic lesson in how model architecture can bite you. Quorot is generally a great algorithm for KV cache compression, but on the 1.5B and 7B Quen models, it completely fell apart.
A catastrophic failure. Why?
It comes down to the model's design. Those specific Quen models have these enormous bias terms in their key projection layers. This creates extreme outlier values in the key cache. Quorot quantizes on a per-token basis, so these huge outliers just completely overwhelm its scaling factor, and the quantization becomes, well, useless.
So it's a detail of the architecture, a huge bias term, that completely invalidates one of your optimization tools.
It's a perfect example. It shows how model-specific these things can be. The other algorithm, KV-Quant, worked fine because it uses a different method per channel quantization, which is more resilient to those specific outliers in the Queen family.
Okay, let's zoom out from the algorithms and look at the external factors. Why do we see so much variation in results even with the same quantization method? It seems to come down to two things: how hard the task is and where the model came from.
Absolutely. Task difficulty is a huge driver of failure. The harder the problem, the more steps it takes to solve, and the more chances that accumulated quantization error has to throw the whole thing off track.
You had a great analogy for this.
It's like balancing your checkbook versus doing your complex corporate taxes. For the checkbook, that's GSM 8K. A small rounding error from quantization probably doesn't matter. You still get the right answer.
Right.
But for the taxes, that's AME 120. That same tiny error, accumulating over dozens of steps, can cascade into a massive failure. Your final number is just totally wrong.
And the paper put numbers to that.
It did. The 32B model on the aggressive W4A4KV4 setting. On AME 120, the hardest task, it dropped 3.9%. On GSM 8K, the easy one, it dropped 0.0%. Nothing.
So that's the 4 times worse figure. The complexity of the reasoning path just exposes the error.
It lays it bare. And the other factor is the model's lineage, or its pedigree.
Right. Research question 4, how the model was trained.
Exactly. They compared 2 models from the same Quen base. One was trained with distillation, the other with reinforcement learning, and they had different strengths. The distilled model was more robust to KV cache quantization, but the RL-trained model was more resilient to weight and weight activation quantization.
Which implies that the training recipe itself fundamentally shapes the model's internal structure, making it vulnerable to different kinds of noise.
It sculpts the model, yes. And they saw the same thing comparing different model families. They took a Quen 7B and a Llama 8B, both distilled with the same data. Quen was a bit better for weight only. The Llama was way more resilient to KV cache and full WA quantization.
How much more resilient?
For that super aggressive W4A4 KV4 setting on the hardest task, Llama dropped 11.4%, which is bad, but Quen dropped a staggering 20%. So the base architecture you start with matters just as much as how you fine-tune it.
Okay, let's get into the pure engineering trade-offs. The big fear with quantization is that you save time on compute, but the model just compensates by thinking longer, generating more tokens, which cancels out your efficiency gains.
A critical question. And figure 3 in the paper gives a clear answer. For well-behaved quantization, so 8-bit or 4-bit weight only, the answer is no. If the accuracy drop is minor, the output length stays the same. You get your speed boost.
But there's a catch.
There's a catch. When you push into those really aggressive logit schemes like W3G 128 or W4A4 KV4, especially on the smaller models, then yes, the model starts producing longer sort of compensatory reasoning chains. It's trying to work around its own internal noise, which slows everything down.
So the lesson is, don't get too greedy on the bit width. This brings us to probably the most important part for deployment strategy, the scaling effects in Figure 4. How does a big compressed model stack up against a smaller, full-precision one?
This is where the strategy really changes. The results are a huge endorsement for scaling up your model size and then compressing it. A large, low-precision model consistently beats a smaller, full-precision model, even if they take up the same amount of memory.
Can you give us a concrete example?
Absolutely. A 32B model, quantized down to 3-bit, takes up about 14.5 gigabytes. That's roughly the same size as a 7B model running at full BF16 precision.
Okay, same memory footprint.
Same footprint. But on the live code benchmark, that 3-bit 32B model was about 17% more accurate than the full precision 7B model. So for the same hardware cost, you get a much better model. That's a huge win for accuracy size scaling.
And what about for accuracy versus latency?
For latency, the 4-bit quantized models were the clear winner. They offered the best trade-off. You maintain most of the accuracy of an 8-bit or BF16 model, but you get that maximum generation speed. The 4-bit zone is really the efficiency prize, if you can just manage that risk.
Before we finish, we have to touch on calibration data. It's often this overlooked detail, but the paper found a massive sensitivity here for reasoning models.
It's a huge finding. A lot of older research suggested you could just use generic data like Wikitext2 for calibration and it would be fine. But for these reasoning models, that's not true at all. The pattern of activations a model generates when it's solving a complex math problem is completely different from when it's just processing text. There's a domain gap.
And one algorithm in particular really suffered from that gap.
GPTQ. Because it relies so heavily on that calibration data to fix its own quantization errors, when they switched the calibration data for a 1.5B model from generic text to reasoning-specific math data, the accuracy for GPTQ jumped by an average of 9.8%.
A nearly 10% gain just from using the right calibration data. That's an essential lesson for anyone deploying these models.
It absolutely is. It proves that for reasoning tasks, this domain gap is real, and for certain algorithms, ignoring it is fatal. It also reinforces why EWQ and flat quant are better defaults. They were much less sensitive to that shift.
This whole study really feels like an essential roadmap for anyone deploying LLMs for reasoning. The summary seems to be, if you need guaranteed mission-critical performance, W88 KV8 is your path. It's lossless and safe.
That's your safe harbor.
But if you're chasing peak hardware efficiency, 4-bit weight only, W4A16, is that high-risk, high-reward path, but only for large models where you've chosen your algorithm and your task very carefully.
It really moves us from guesswork to actual guided engineering. But the paper also leaves us with this one final open challenge. It brings us right back to that problem of accumulated error. They found that while making a model take more reasoning steps usually improves performance.
For both full precision and quantized models.
Right, but the rate of that improvement drops off much, much faster for the quantized models.
So the longer the reasoning chain gets, the less benefit the quantized model gets from that extra thinking time.
Exactly. The quantization error just keeps piling up and eventually starts to hinder the reasoning process. So the big challenge for the community now is to figure out how to mitigate that accumulation. How do we make it so that quantized models can get consistent performance gains even over thousands of reasoning steps? Whoever solves that will unlock the next level of efficient, powerful AI reasoning.